Okay, awesome. Hi, everyone. I hope you all had a relaxing spring break. I know I'm a little sad that it's over, but we're back and it's gonna be great. Our lecture today is gonna be all on animation. So hopefully that'll be really helpful for all of your final presentations if you're planning on like animating or simulating anything of any sort. Yeah, so a couple announcements. The project proposal is due Wednesday before lecture. So like come to office hours, ask us questions about like LaTeX or like what you're working on or anything like that. The deliverable like for the final project is due April 19th, and the presentations are going to be like the last two lectures on the 19th and the 21st. These dates are still kind of, they're not set in stone. So like, yeah, we'll keep you updated on that.
Yeah.
And then, yeah,
Oh,
go ahead, James.
I just want to add, your boy kind of realized that there's like 4 extra weeks in the semester that I didn't notice. So I had us originally doing our final project in like 1 week, and I was like, oops. So this I added 1 extra week, but we also have room for another extra week before dead week 2 or RRR week. Apologies. So we'll see how it goes. If we feel like on the Friday before the 19th that you need more time, then we'll add an extra week. But as of right now, we're set for the 19th and the 21st as the time you present your projects, but that may get pushed back a week.
Yeah, awesome. And yeah, then fill out the attendance link. Cool. Yeah, so quick recap. We're gonna split you up into breakout rooms like usual. Kind of just like go over how our final project proposal's going, slash like how was your spring break? Also like are you planning on using like classes in your final project? That's what like we went over last time is like object-oriented programming. So maybe discuss like are you planning on using that in your final project? So let me make some breakout rooms. How many people do we have? I'll just make 2. Cool. Okay. Awesome. Yeah, so hopefully it was nice talking to everyone. Does anyone have anything they want to share about maybe like what they did over spring break or if they're planning on using classes in their project proposal or like anything about your final project? Cool. No worries. Yeah, but if you have any questions about like LaTeXing or like how to do anything for your final project or any logistic questions, come to our office hours. I have my office hours right after this lecture, so feel free to just stick around for that. Cool. Okay, now on to animation. So here's an example of a kind of animation that you can do. There's like tons and tons of different animations you can do. You can animate pretty much anything. This is like a special package for erosion animations. This is something that you go over in EPS 109, which is a class that Emily and I both took, and that's where a lot of our animation kind of background comes from. So yeah, if you want to learn more about animation, I definitely recommend taking that class. And this is kind of an example that someone did as their final project for that class. Yeah, so this animation is showing the erosion of Crater Lake. And it's pretty neat. You have kind of the 3D model of it and then kind of like a topo map on the right. So you all probably won't be doing like an erosion animation like this, but it's pretty cool. And if you want to learn more about how to like use this like special erosion package software, like come to me or Emily's office hours and we can totally show you. Another example that's pretty cool and it's using like random walk is this infection simulator that someone else also did for their EPS 109 final project, which is like pretty relevant given like the current times. So this is an infection simulator. So kind of showing the infected, the disease recovered and susceptible, with like the random walk of like these particles like representing people. Kind of goes to show like there's a really wide range of things that you can animate. Awesome, yeah. So not only can you animate a lot of different things, but there's lots of different ways that you can animate things. Today, Emily and I are going to focus on matplotlib.animation.ffmpeg writer, which is what we use in EPS 109 to animate things. The documentation can be found at this link. You can also just look up like matplotlib.animation.ffmpeg writer documentation and it'll pop up. So that's what we're the most familiar with, but there's like a ton of different ways. Another common one is matplotlib.animation.func I'm personally not as familiar with that. You can totally check out the documentation if you want to learn more about it. And there's also like VPython and stuff, which I'm not super familiar with, but is also a really common way to animate things. Cool.
Oh, okay, so for like kind of an example that we'll walk through to like teach you guys how to animate things is this example of a moving sine wave. And so basically you can see that like for each like pause frame, you already know how to plot that. Like you can just do like a scatter plot and do your like sine or cos function, and you guys already know how to do it. And with animation, you basically just like pause each frame and save it to like an MP4 file so that it all like is put together into an animation. And so we can walk through like how to do that now. Yeah, so for using Ffmpeg, like the first step, as like we've done with a lot of other plotting, would be to import necessary libraries. We have like the usual like NumPy and Matplotlib. And then like to use Ffmpeg writer, you would also add this line of from matplotlib.animation, import Ffmpeg writer. And we'll also have to like download this on your computer since it's not just like built into Jupyter notebooks. And we'll have like an announcement, and like you can also find like steps on how to download it in like the animation guide that we just uploaded. Yeah, so basically to use Ffmpeg writer, the first steps you would kind of do is you would first like kind of initialize the writer. As you see in like the first few lines of code, we have like metadata, writer, and the figure. And then like the next like with loop is kind of the whole like animation. And so if you see like in the blue rectangle, like this is just like the normal code that you would use to plot something like a sine wave. And so like the like kind of the most difficult part of animating things, like you guys already know, is just how to plot. And like the added structure around it just helps you save the images and like combine them. But yeah, we'll go through like the structure more in the next few slides. Yeah, so like from the previous slide, we saw like metadata is kind of more optional, and it's just basically when you click on any file you have saved on your computer, you can click like get more info, and like stuff like the title of the file, like the artist, any comments will pop up. And so metadata is just so if you want to like store any additional information about your file when your animation saves later. And so for writer equals ffmpeg writer, this line just helps initialize the writer. And this is really important because this is what actually saves each frame to the MP4 file, because otherwise we would just have like individual plots. Yeah, and here like the argument FPS just stands for like the frame rate per second. And so like if you increase this, you'll have more frames per second. And so you can kind of play around with that. And as we saw like before, when we were learning about plotting, we just initialized the figure of our plot using plt.figure. Yeah, and so now if we look at the with loop, basically like the loop like with statements, you just use whatever like the argument is for the with statement and like to do something. And so basically this is saying like with the writer saving function, we will do everything that's in the loop. And so the structure for this is just doing with writer.saving. You just need to specify like the figure that we initialized before. And the name of the file is also really important. And like this writer will by default just save the animation to whatever directory your like Jupyter notebook is currently in. So like at the end of running this, you'll just see the file like saved already. And it's also really important to like whatever file name you want to do, the end of it should just be like .mp4 and the file name has to be a string. Yeah, and so like the kind of new lines we see here are like plt.clf, and this just stands for like clear figure. And this helps clear the frame. So basically how this with loop works is that like nf equals 100 because we say like that's how many frames we want to pause at. Because like the writer for like every frame that we pause at, it'll like save it to the animation. And so at the end, it'll just play all 100 frames. And so for each frame, we basically want to plot like the cosine plot, which like you guys don't have to really worry about the like specifics of this sinusoidal thing. It's kind of just like arbitrary. So basically you like on your for loop, you plot whatever data you want. Then you would clear the frame so that like any data from the previous frame is like gone. And then you plot like the data, like how we normally do using plt.plot. And then you can also do plt.show just so like you can check it in Jupyter Notebook if like the plot looks good. And then next you just do plt.draw, which will actually draw the plot like to your figure and not just like in your Jupyter Notebook. And then you also have plt.pause. And this basically will just pause the figure at whatever frame it is for like however many of seconds. And so kind of the default we use is like 0.1, but you can like play around with that as well. And then also really important, like at the very end, doing writer.grab frame, which will actually just kind of grab the frame and like save it to the MP4. And so obviously it's kind of like there's like a lot of steps and it might be kind of hard to remember. So like a lot of times it's just easier to like kind of look up an example or just go back to like these slides for reference. Like we definitely don't expect you guys to just like know off the top of your head like every single step. But yeah. Okay, and so that was using Ffmpeg writer like the previous slides. And so this slide is showing how you would do like the exact same thing using Ffmpeg animation. And so like we won't go too much into detail here, but if you guys want to use it, like feel free to like come back to the slide and look at it more. But it's kind of like the same steps of like first initializing the figure and axis for like the animation. And then just like, you know, also defining the function, like you see here, they defined like the sinusoidal function and the animate function here. And yeah, it's just like different syntax doing the same thing. Okay, so that was how to animate like using 1D array of data, which is like the kind of simplest way. But a lot of times, like as we saw in the erosion example before, or like there's just a lot of two-dimensional data, like also like any data stored in an array, you might want to do like using like a 3D kind of grid. And so this is like another example of it. Yeah, so this is kind of like the same ideas from before, but this is just, we're going to go into like how you would change the code if you wanted to do it on a 3D axis instead. Okay, yeah, and so kind of like first step again, you would like import all your needed libraries. And since we're doing like a 3D plot, we also need to like import axes 3D and also import a color map. And like if you see here, like the top line, like the percent matplotlib osx, it's kind of an optional line, but if you include this, it'll just have like a pop-up window where you can like see your animation getting created in real time. And so that's definitely an optional line. Like if you don't have it, it'll just save the file to your directory. But this might be helpful, like if you just want to like see it happening as it's plotting. Yeah, and then like you see like we still have the same 3 lines of like metadata, writer, and fig. Okay, yeah, so since this is like a 3D axis, we need to like take a few more steps to initialize this. Like before, we kind of just had a 1D NumPy array, so we didn't really need to initialize anything. But since it's 3D, like these lines just kind of help initialize the 3D mesh grid using mp.linspace. And there's also like more references in the Python plotting guide for how to do that. But yeah, so here like X and Y are kind of the 2D axes of the matrix. And then the Z-axis kind of like actually holds the data. It's kind of like the 3rd axis. So this is like the vertical axis that we see on like the 2D sine wave from before. Okay, yeah, and so this is the like actual animating part after we first like initialize all of our like writer and the figure, and we kind of initialize our axes. We then kind of go into the animation loop. And again, this starts with like similarly with the with statement and like the same like figure and like the name of your file as an argument. And so we still do like number of frames equals 100. And for each frame, we like plot the data. And so here, you can see we use a double for loop because our data is now a 2D array. And within the double like ij for loop, we update zij, which is just like the values of the sign like matrix we had before. Since like XY was our axes and Z was kind of like the vertical information. And also like, don't worry about like the mathematical stuff going on in like the Z matrix. It's just showing you can update it to whatever you want it to be. And like, just depending on like where it is in the like double for loop. And so after you kind of update your data in each frame, you would then do the same steps of like clearing, plotting, drawing, pausing, and grab frame. But since it's 3D, like we use fig.clear instead. And we also set like our axes to fig.gca projection equals 3D. And then instead of like pld.plot, we use ax.plot surface. And so it's okay if you also don't like really understand like the kind of syntax for plotting in 3D. Like a lot of times, like I still like look all this stuff up too, but like this is just an example so you guys can like come and look at it later and try to like adapt it for your code. Yeah, so exactly like this is like a lot of the same format as the 1D wave, except the data is now stored in a 2D array. So that's why we use a double for loop to update. And then just like kind of small syntax differences of using like ax.plot surface instead of plt.plot.
Okay, yeah, so that was like kind of the setup of like a basic example. So I just wanted to go through kind of like a general setup of how like the general steps that you would take to make an animation, because I mean all the animations are so different. So the first step is like importing the necessary packages, Ffmpeg writer, Matplotlib, that kind of stuff. Also setting up the metadata, the writer, and the figure. Yeah, it's all really important to make sure that your animation works. And then the basic setup for making the animation is using this like with statement, writer.saving, making sure you're using the figure that you initialized, setting the figure name, making sure it's ending in MP4. And then this DPI is just like dots per inch. So it just deals with like the pixelation and like the quality of the animation that you're returning. It's not super important. You can play around with it if you want. And then basically having this big for loop that loops through for the number of iterations that you want your animation to go for. And then inside the for loop, you have code that updates your data and plots whatever you want to plot, whatever you want to animate. Yeah, making sure that you're clearing the figure so that you don't have like leftover stuff from like the previous iteration. Making sure you have plt.draw, so it actually draws and saves to the animation. plt.pause, so that the frame is kind of shown in the animation for a set amount of time. And then writer.grab frame, so it actually saves the frame in the MP4. Does anyone have any questions so far about the general setup or anything we've gone over so far? Okay, awesome. Yeah, it's kind of a lot. I know, like what Emily mentioned before, is that like I definitely get confused sometimes and I have to like look it up because it's a lot of like random steps that isn't really used anywhere else except for animation. So totally okay if you're confused. Yeah. Yeah, and then some quick tips for animating. Keeping in mind boundary conditions and making sure those are initialized and kind of set for every loop. So an example for that is like if the edges of your animation should always be a certain value. So like something you can animate is like heat diffusion. So like if you're animating like the heat equation, let's say you want to have one of your boundaries always at a constant temperature. You want to make sure that when you're iterating and using this for loop that you're not changing your temperature at that boundary. So whether that's making sure you're not updating it or like resetting the value so that the t stays constant at that boundary. Also, we'll be going over differential equations more on Wednesday, but for turning differential equations into code, anything that's like a differential, so like dx dt, can be kind of dealt with by changing your value by like, let's say delta x for each delta t, so like each step in the loop. And so like the smaller your delta t value, the smaller your delta x value, kind of the smoother your animation's gonna look, but also the longer it's gonna take to run. So kind of a trade-off there, something to keep in mind. Yeah, this is really helpful for like differential equations. So like kinematic equations, heat diffusion, lots and lots of other things. Last couple points, Google is totally your friend. A lot of animations, like someone's done something similar before. So look it up. Totally helpful, whether that's like documentation or like Stack Exchange or something like that. And also Emily and I made an animation guide, Jupyter Notebook, that's available on B courses that kind of goes through a bunch of examples on how to animate in like 2D, 3D. So check that out too.
I'm sorry to interrupt. Do you think you could, like at the end of the lecture, do you think you could show what the animation guide notebook looks like so that they could see it?
Yeah, for sure. Yeah, so now we're gonna do a quick demo. So let me pull up my Jupyter Notebook. Okay. Where did it go? Okay, cool. Okay, so the demo that I'm going to be doing, I already have it written out because it's kind of a lot to write, but I'll go through it step by step, is a pretty simple like 4-bit simulation. So like we talked about before, we want to make sure we're importing the necessary packages. This first line is basically like making our plotting look better. by like having to be retina, not super important. And then this is making so that when we're plotting it, it's like a separate pop-up window. So like we can see it animating and plotting in real time. So I think that's kind of fun to see. This is the Mac version of it. I think for Windows, it's like Qt or something. Yeah, not super important. Setting the metadata, the writer, and initializing the figure. For this example, it's going to be super, super basic. It's just a planet orbiting a star. So I set these constants. They don't really have any like physical meaning. They're kind of just values that I know work. So we're going to go with that. Setting the initial positions. I have them as two separate arrays as the initial position and the initial velocities. This is kind of just setting like time data. I'm going to set the initial time as t0, and then I'm going to have it run for 10 time, whatever that means. And then my time step is going to be 0.005. This value, I kind of just played around with the animation on like what makes the smoothest curve, and like didn't take too long to run. So this is like a good default value, but again, like mess around with it, see what works best for your animation. It could be like a totally different value. And then I'm just like initializing all these lists for data that I want to store to later plot. Yeah, this is the function that I'm going to be using to get all my position data for the orbit. Again, we're going to be going over like differential equations later, but this is like pretty basic. We're just calculating the force of the force acting on the planet by the star. NP lin alg norm is basically just calculating the normal of this vector, and then MP concatenate is basically taking these two arrays and making them into one. So just because it's kind of easier to deal with one array rather than two. Awesome. Yeah, and then so for this example, what I did is looped through and obtained all the data that I wanted, and then later looped through and plotted it. So I basically just made this giant list of all my positions. And then later I went through and looped through that list and plotted it like step by step. So yeah, there's a bunch of different ways you can do it. This is just the way that I chose to do it. So I'm saying that while my index of t, my time, is less than like the time limit that I wanted, I'm going through, I'm calculating the kinetic and potential energy because I'm going to deal with that a little bit later. I'm appending my positions to my like position lists. And then I'm running the function that I defined before to calculate the forces on, or the force on the planet. So this is using the Runge-Kutta method for kind of like discretizing this differential equation. Not super important. We'll be going over different ways of doing this later, but this is just the way I did it for this example. So it's basically just going through and updating the positions for each time and saving it in a giant list. So to actually animate it, again, we're going to initialize the figure and then use this like with statement with writer.saving the figure, the name orbit.mp4, making sure that we're clearing the figure for each iteration in the for loop. I had it so I'm just iterating through the length of how many positions that I have. And then I'm just plotting all my positions data up to the index that I'm at. And then something else that I did that I think makes the animation look a little bit cleaner is I set the boundaries. So the boundaries or the axes of my plot are the same through all frames in the animation. So instead of it like the animation frame like changing size, I set it to the minimum of my like position list and then the maximum, so that, yeah, it's not changing size. Then plt.draw, plt.pause, and making sure that I'm grabbing the frame. So let's see, if I just run this, yeah, so when you run it, you'll get this pop-up window, and that's what like the Matplotlib OS X does. I'll run this. And then running that frame, you'll get this pop-up window that'll show you it making the animation in real time. And it kind of takes forever, and it's really annoying because you can't tap away from it because it'll just keep reappearing. So thankfully, I already ran it, so we don't have to wait for it. So let's see, yeah. So once we let it run all the way through, you get something that looks like this. So it just goes through and plots the orbit of the planet around this star. And so if you change like the frames per second or your time step or anything like that, your animation will like go at a different speed. So that's totally something that you can mess around with. Does anyone have any questions about that so far? Cool. So kind of a different variation of this is instead of just like plotting the orbit, we can have it so it plots like the actual planet and then like a tail of the orbit, which I think looks kind of cool. This is just code to plot the tail. And then this is making it so I'm plotting the planet position for each iteration. So again, if we run that, I won't run it because it'll take forever, but I already have the animation saved. It looks something like this. So instead of plotting the whole orbit, we just see like the planet going around with a little orbit tail. And I think this tail thing is kind of cute because it like kind of shows you how fast the planet's moving based on like the length of the tail, which I think is kind of fun. Yeah, and you can totally change the tail length. I set it for 50 in this example. Just something cool you can do to make your animation look more fancy. And then the last little demo that I have is plotting two plots at the same time. So before, I also saved like the kinetic and potential energy, which are calculated the normal way. So I'm also saving those as a list. So something you can do is you can plot two at the same time. So we've done this before using AX and having subplots. So we can go through, it's kind of the exact same thing, except using like AX0, AX1, making sure we're clearing both and then plotting on both. And using the same feature is only plotting up to the index that you're at in your for loop. So you're not plotting everything at the same time. Yeah, so if we run that, we get an animation that looks like this, where above is the orbit of the planet around the star, and then below we have the kinetic, potential, and total energy of the system, which is pretty cool because we see that the total energy is constant, which is exactly what we should see, which is pretty exciting. Yeah, so you can animate multiple plots at the same time. You can even like animate multiple planets orbiting at the same time, multiple objects. Yeah, this is just a really basic example of just having one planet orbit a star. Yeah, does anyone have any questions or want me to go over anything again? I know I went through that kind of quickly. It's kind of a lot.
I just want to add that we'll be covering more simulation stuff too. So don't worry if this is like a lot like right at the gate. We're gonna have like a couple lectures where we talk about simulations and a little bit more in depth, and we'll review this over and over again and kind of get like the basic ideas down, so that, because simulations, especially in the world of COVID, is kind of like what everybody does for research right now, because nobody can do actual experiments. So we want to make sure you understand how a simulation works. But yeah.
Yeah, totally. It's confusing stuff, and it's a lot of like weird syntax stuff. Yeah, so we'll totally be going over it again. Awesome. Okay, we have a little bit of time. Emily, do you want to go over the other example that we have?
Yeah, sure.
Okay, cool. Let me share my screen again. Sorry, my computer's being weird. 1 second. Okay, cool. Let's see. Can you see my screen?
Yeah.
Okay, cool.
Okay, yeah. So like just for like going over another example, just because I feel like the best way to kind of learn like these things like animation, where like most of it is just syntax, is just to like have a bunch of examples that you can look back at later, and then you can try to like use it for your own ideas and like whatever thing you're trying to simulate. And so this example was just to simulate a forest fire. And this is actually like the final project I did for like EPS 109, which was like we had to do like any simulation on like anything really. So I chose to do one on like forest fires, and I wasn't just like an expert on forest fires going in. I found like just like this research paper online that kind of talked about how you would go about simulating it. And I just like based it off of that. Yeah, so we have like the same steps of like first importing all the necessary libraries. And then, so like for forest fire, I had like these probability parameters to decide like if like a tree was burning, like if its neighbor should also start burning as well. And like to make things easier, I made my own like display function, which is just kind of like what goes inside the with animation loop. That basically just like helps update my data by doing a double for loop, since the data is like a 2D array. And then I do like the similarly like clearing the data, then doing by plotting it by doing imshow, drawing the data, doing plt.pause, and then doing writer.grabFrame. Yeah, and so like these steps were kind of just initializing the matrix and also like dealing with boundary conditions, just because like since the trees like on the border of the matrix don't really have all their neighbors, I just decided to make all of them empty dirt cells to like simplify it. So this is like what we mean by boundary conditions, just keeping in mind like what should happen at like borders or like any initial conditions. Yeah, and then here we just have like the usual like metadata, writer, like initializing your figure, and then like doing like with writer.saving. And so like I had like my number of steps I wanted, and like to simplify things, I just had like a if statement for like if t mod 10 is 0. So basically every 10 frames I would save it so that I wouldn't have to like wait forever, and it would just like speed things up a bit. Yeah, but it's like not too important here, but it's just basically like double for loop updating my data, and like there is some stuff to make it like unique to this simulation. And then like at the end, just making sure to do the same like draw, pause, and writer grab frame. Yeah, so now we can like see how it turned out. Yeah, so the one on the left is like exactly what the code in the previous slides does. And like the video on the right was when I like made the matrix a lot bigger and like changed the parameters around. So you can see that just like changing some parameters and like animating things can have really cool effects. But yeah, so don't worry if you don't like understand the logic behind like say a forest fire. It's just so like you can look back at more examples later.
Yeah, and I think that's all the time we have. So if anyone has any questions, feel free to ask them. If not, you're free to go, I guess.
Oh, actually, hold on. Before anybody leaves, really quickly, I just want to announce or remind you one last time, final project proposals are due before lecture on Wednesday. So please submit those, LaTeX them, and you will be presenting them on Wednesday first thing. So don't worry, no slides needed or whatnot. Just bring your LaTeX document or PDF file, have it written up, and just give us, you're going to give us like a 2-minute like maybe 1 to 2 minute speech on like what you're doing. Very low pressure, but just make sure you get those written up so that you know what you're talking about. Please come to lecture. I'm going to send out an announcement as well. We need everybody there. One, because it's respectful for everybody else, but two, because we want to see what everybody's doing. But yeah, thank you for coming, and I hope everybody enjoyed the lecture.
Thank you.